plus 4?
So I'm doing formal charge. Sorry I missed the beginning of it. The formula that we're using is here. Formal charge is equal to the number of valence electrons minus the number of non-bonding electrons plus 1/2 of the number of bonding electrons. And you do this for every atom. So I'm going to do more than one, but this is where we are with this example. All right? So the first oxygen I did was 6 valence electrons minus 2 non-bonding electrons plus there's 6 bonding electrons, so that's 3. So that gives me a formal charge of 1 on this oxygen. Next is the carbon. I have 4 valence electrons minus 0 non-bonding electrons plus there's 8 bonding electrons, so half of that is 4. So that gives me a formal charge of 0. Jason.
Never mind.
Okay, so next I'm going to do oxygen 2. So I have 6 valence electrons minus, I have 1, 2, 3 times 2 is 6 non-bonding electrons plus I have 2 bonding, so half of that is 1. So I have 6 plus 1 is 7, so this is negative 1. Yeah.
Could you go over how you count valence electrons?
Yep, left to right on the periodic table.
Oh, it's not from there.
No. 1, 2, skip the dip, 3, 4, 5, 6, 7. Yep. Okay, now when I add all of this together, I get 0. Okay? Now, that's structure A comes to 0. The question is, which is most stable? Structure A or structure B? Okay, because there are 2 ways that I can do this and meet all of the criteria for a Lewis dot structure. The first looks like this. So that's what this one looks like. This one looks like this. And so the question is, which one is most stable? Everybody with me? So now we're going to do this one. The first oxygen is 6 minus 1, 2. So that's 4 unbonded. Minus, there's 4 bonded, so 2. Oh, sorry, plus 2. Plus 2. So that's 0. Next, carbon. 4 minus, there are 0 unbonded plus 8 bonded, so that's 4, 1/2, right? 1/2 of 8 is equal to 0. And then the second oxygen is 6 valence minus 2 sets of pairs, so that's 4 plus, I have 4 bonded, 2, so that equals 0. That's 0. Now they both equal 0, but structure B is more stable because it has the least formal charges, even though both structures satisfy all the octets and have the correct number of valence electrons. Now, the criteria for formal charges is as follows. 1. Formal charges of the molecule must add up to 0. 2. The sum of the formal charges of an ion must add to the charge of the ion. That makes sense, right? Three, small or zero charges I'm going to move up, hang on atoms are preferred to large ones. And lastly, 4, when formal charges can't be avoided, and this is important, the negative charge must reside on the most electronegative atom, not in the center. And I'm about to show you an example of this. Okay, so we're going to calculate the formal charges here. It's pretty easy because all of the hydrogens are the same. So the carbon is going to be 4 minus 0 plus 1/2 times 8 is 0. And each of the hydrogens are 1 minus 0, no unshared pairs, times 1/2 plus 1/2 times 2, which is 0. This molecule is neutral and has no formal charges. Similar to this molecule here. Okay? So it's stable. All right, let's take a look. Choose the best structure based on formal charges. So I go through, and so this is where I started going like, this is a lot of work. This just seems like a really extraneous, a lot of work. And so that's why only one of these problems has shown up in 3 years. Because it's a lot of work, right? Okay, so I want to be clear about something. The hardest part about this is remembering the formula. Once you remember the formula, it's not, remember what I said, every problem on this test is not a challenge to do the problem. It's a challenge to say, do you understand the concept and how to do the problem? Okay? It's very important that you know that. They're not asking you to spend 15 minutes on one problem. They're saying, do you know how to do a formal charge problem? Do you know what it means? Can you do it? Okay, good. Take 2 minutes and do this problem. All right? Okay. So, sulfur, they're not going to do it. It's not going to look like this. But there's not going to be 3 of them. You are going to have to draw the Lewis dot structures. They're going to say, like, draw the 2 different structures for this element and choose the most stable one. And you've got to know, oh, it's a formal charge problem. Okay, I'm just going to draw the 2 of them and then pick the most stable. And they probably have 3 elements in them, right? And it's going to be really obvious which one is right. But if you don't know how to do formal charge, or that you need formal charge, you can't do the problem. Does that make sense? All right? Okay, so let's look. So here's sulfur, 0, oxygen, 0, and oxygen, -1. Net charge, -2. Well, that's weird. Net charge negative. Oh, because there's 4 of them. Right? Sulfur and oxygen, +2 and -1 net charge. They both have the same net charge. So what's the problem here? Well, we're going to see which structure is better. So while structure 1 here, net charge is -2, net charge is -2. Structure A minimizes the formal charge. It violates the octet rule for sulfur. Okay? We'll see why this is okay later. Also, what makes 2 of the oxygen atoms more special in that they have a double bond, while the others are only single bond. Structure B has formal charges on every atom. -1, -1, -1, and the +2 on sulfur, which is kind of large. Could both the structures play a role in understanding the true nature of the sulfate ion? I purposely chose a different structure that raises these types of questions in study and think about. The next topic will address some of these issues. So we're not actually sure which one is going to be right, except that the sulfur, the +2, is kind of challenging here, right? That doesn't look right. Okay, so let's take a look. Assign the formal charges to each of the atoms and the following structures and show your work. So do this now, please. The D here is for double bond, and the S here is for single bond. And then go on to number 2, check your answers, and go on to number 2 and choose the best structure based on formal charges. Yeah, Jenna.
How'd you get 3 for the first column?
Here.
Yeah, when you did carbon.
So carbon has 6 here. So this is going to be half of that.
I thought it was only a double
This is a triple bond. Does that make sense? Okay. I wish I could zoom in, but I can't zoom in. Okay, very quickly, we're just going to do an expanded octet so that you have that for your homework. So the example is xenon hexafluoride, fluoride 6 hexafluoride. So we have xenon, which has 8 electrons, and then 6 fluorides, which is 6 times 7, which is 42 electrons. So that's a total of 50 electrons, which is 25 pairs. Right? So I'm making my wheel. So I'm going to put xenon in the middle, and then I'm just going to put my fluorines around. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Oh, let's see. 6 times 3 is 18, and 6 is 24. Oh, 25. There you go. 25. So it works out perfectly. All right, 25, and my extra pair goes in the center. All right, because the extra pair goes on xenon. So it works out perfectly. All right, there you go.